All right, guys, so welcome to lecture 3. And I think if you recall, we finished off with the introduction of the natural exponential function as well as natural logs. So we'll start off there. But please, I think it's important that you engage with the material in our Moodle classroom. All right, there's plenty of material there in terms of notes, videos, tutorial exercises, mock tests. So please start to go through these. And also please be reminded that next Friday, which is the 7th of March, we will be writing your first minor test, right, for this course. So we'll have that information up together with the content for that test. So please, again, engage with the material that is in our Moodle classroom. All right, so let's proceed with this video and let's see what we can learn and that will be useful for us, not just in the exams and tests, but also in engineering. So if you look at the natural log function, right? So the log functions, which we studied in school, which we studied under the section of inverse functions, if you look at it in metric, now we're going to introduce what we call the natural log, which we did last week. And the way we define that as y equals to ln, ln x, if you have a look here. And that is equivalent to the general log x, but base e. And if you recall here, x has to be a positive number. You can't take the log of a negative number. So you'd have an issue there. Remember log graph. I'll present that shortly. And this number e, you'd remember, is named after the famous mathematician. And when I say famous, I mean very famous. The strange thing is many people have not heard of him. So how do you define him being famous? And that is Euler, E-U-L-E-R. And if you look at your calculator, you'd actually see there's ln x in your calculator, and inverse of ln x, you got e to the x in your calculator as well. All right. We also note that ln of e is 1, and then ln of 1 is 0. This was discussed last week. So if you look at the exponential graph, we discussed that as well. Y equals to e to the x. If you look at the one at the top here, the dark blue graph, right? And then its mirror image about the line y equal to x is y equal to ln x. So you got y equal to e to the x, and then you got this pink graph y equal to ln x. They inverses of each other. So they are mirror reflections about the line y equals to x. I think that's important as well. Okay, and some rules. Well, we went through the rules for the general logs, log, right? So the similar rules apply because it's change of base. So the ln of the product is, well, ln A plus ln B and so forth. And we know the power one is very, very important. Ln of A to the power m is m ln A. And that I think we know. All right, so it's pretty straightforward, not difficult. But it's the applications that are important here. So let's run through this and see whether we can tackle a few questions. Now, a few things. Look at what's in orange here. It says e to the ln x is equal to x. Now, I'm going to be crude in the sense that I'm not going to be elegant in my speech for now. And this is going to help you remember. And you might think, well, mathematics is an elegant subject, but what are you talking about being crude? Well, let's put it this way, right? This is crudely speaking. When E meets ln, they seem to, I'm not going to use the word cancel. No. Let's think of it as just dissolving because they're inverses of each other. And what's left over is just the x that you see there. That is not mathematical talk, but it's something for you to remember. Okay, so when E directly meets ln, boom, and you have x. So if you have a look at, say, for example, this one over here, and they say simplify, you notice, well, the first thing is e to the 2 ln x minus x. You can write that as a product of e to the 2 ln x times e to the minus x. So I think we're all happy with that. Right? The problem here is the 2. We want e to meet ln directly. So the 2 pops up there. that becomes e to the ln of x squared. Power law, reversed. But when e meets ln, boom, what's left over? X squared. So final simplification is x squared times e to the minus x, which you can write down as x squared over e to the x. And there you have it. It's quite simple. So here we're just emphasizing that power rule in reverse. 2 ln x e to the ln of x squared, right? So you'd remember that. Excellent. So let me just pause there for a moment. Right, and let us continue. So let's look at, whoa, what's this? So now we say solve for x, but if you have a look very carefully, the left-hand side reminds ln of x minus 3 plus ln of x is equal to e to the ln of 10. Hang on, let's start with the right-hand side. E meets ln. What do we have? 10, right? Simple. On the left-hand side, that reminds me of ln A plus ln B. And we know from the rules, it's the product rule. So that'll be ln of A times B, A being x minus 3 and B being B. So that becomes the product. So now we need to get rid of the ln. We can't just drop the ln. This is not ln times something. It's ln of, right? And it's equal to 10. So how do we get rid of ln? Well, we call on its inverse. So we exponentiate, as I mentioned. Exponentiate one side, you've got to exponentiate the other. But when e directly meets ln, and what pops down is that here. But what is this number over here? It's just a number. You can evaluate that in your calculator. It's a constant. Bring it to the left-hand side, and you see, what do we have? We have a quadratic equation, right? Which, of course, cannot be factorized. So if I want to go back, I'd forgotten it's x into x minus 3, yes? Minus e to the power 10 equals to 0. So that becomes x squared minus 3x minus e to the power 10 equals to 0. And we could say, well, if this is now a quadratic, not if it is, then we know that a is 1, b is minus 3, and c is this very strange number, e to the minus 10. Nothing strange about it. It's a number. Use the quadratic formula, x equal to minus b plus or minus square root of b squared minus 4ac all over 2a. Hoo-hoo, that went quick. Boom, solve for x. All right, so take a look at that. Make sure you understand it. Make sure you complete the question. This should be straightforward, nothing difficult. All right, great. Okay, so what have we here? Now we have an equation, looks all exponential on the left-hand side and equals to a constant pi. Now, if from my point of view as a theoretical astrophysicist, I'm interested in pi, but pi mesons. My wife just reminded me the other day on the discovery of pi, the pi meson theory by the famous Japanese physicist Yukawa. Right? Please Google that. And his quest to understand these subatomic particles. So we have particles like electrons, protons, neutrons. We have antiparticles. So we have, say, for example, a positive electron. You knew that? No? Yeah, well, now you know. So we have a positive electron, we have a negative proton, and we have what we call an anti-neutron. And the big question to ask is, can these particles be broken up into smaller parts? Well, protons and neutrons we know can be broken up into quarks. Electron seems to be what we would call a fundamental particle, right? So there's no substructure in there. But there are other particles, like as I mentioned to you, these mesons, we have bosons, we have hyperons, we have leptons. These are families of particles. We have W particles, we have Z particles, as the Americans would say, or Z particles. And we have a whole host of what we call virtual particles. We never told about these things in school, never mentioned. But they do exist and they glue the universe together. Speaking of glue, there's also called gluons as well. Anyway, let's come back to this question. 4 to the power x times e to the power x minus 1. And it says clearly solve for x. So how would we solve for it? How would we separate the x's and try to keep them on the left-hand side? All right. So if I do that, why is the camera on? I don't know. So we could write this as 4 to the power x times 4 to the power 1, agreed, times e to the x times e to the minus 1 equals to pi. Pi is just a constant. What if I told you we can write this now as 4 to the power x times e to the power x times 4 times e to the minus 1. Now this one that is in brackets, that's just a constant, and that's equal to pi. So we can divide out, and we would have something like 4 to the x times e to the x equals to pi all over that product, 4e to the minus 1. Both raised to the power x. Beautiful, isn't it? Aibo, that's a pi, that's a e. Please hold your breath for a while, focus, and are these two equivalent? Pi over 4e to the minus 1 is same as pi e over 4. Now the question is, how do we get to solve for x, where x lies up here in the power? So what do? We take logs on both sides. Yes, that's what we've been doing all this time. Okay, so there we are. From the previous slide, we had exactly the first line, and then to actually get rid of, well, not get rid of the x, but we want to solve for x, we take logs on both sides, right? What we do on one side, we do on the other. The x pops up in front here. That's pretty straightforward. And then what we have here is just a constant. It's just a number, so we divide both sides by that number. Boom, and we solve for x. It wasn't difficult. So the next question people are going to ask me is, how do I know if I'm using log, log, general log, or ln, ln? Does it matter? Yes or no? Think about it, try ln, solve for x, and see whether the answer is the same, right? So this is very, very important. Please check. And I think that's something that we need to also basically quantify for ourselves, see whether we get the same answer using log, log, the general log, or the natural log, ln. Perfect. Ooh, what do we have here? Oh, this is easy. 3 to the power 2x minus 2 times 2 to the power 3x plus 4, right, equals to 3.2, 3 comma 2. There's the solution, x equal to 0, 0,1374. How do we solve for x? Again, it's very similar to the previous question. You sort of break up the product, That's 3 to the power 2x times 3 to the minus 2 times 2 to the power 3x times 2 to the power 4. Then group the x's and then take logs on both sides, right, to bring the x to the front. Try it. It's very similar to the previous question. Straightforward. But you have to do it. You can't just look at a question and say it's straightforward. Write down the answer yourself. Whew. What is this? 8 over x minus 4 all squared minus 6 over x minus 4 plus 1 equals to 0. You see that stuff circled in blue? It's let k equal to x minus 4, right? So then that becomes 8 over k squared. That's a famous k method. My English teacher was called Kandasamy, Mr. Kandasamy, very prim and proper gentleman. So I call it the Kandasamy method. And we multiply throughout and we end up with a quadratic, k squared minus 6k plus 8 equals to 0. And we can factorize that quite easily, and we end up with k minus 2 into k minus 4 equals to 0. So there are two solutions to this here. And we could go k equal to 2 or k equal to 4. And I think we have an issue here, because at k equal to 4, there's no issue, because then we got to go back to the original variables. And the original variables would give me x equal to 6 and x equal to 8. It's always nice to go back and substitute into the original to see if there's any division by 0, and I think that's important. For example, if x was 4, we'd have a problem because x minus 4, 4 minus 4 would be 0, and then we'd have a problem. But some people don't have an issue with dividing by 0. That's a bit weird. Okay, so there we have that. Ooh, this is one of my favorites. It says if ln of root of 1 minus x minus ln of root of 1 plus x equals to y, solve for x. Now, if I look at this, forget about what's in pink here, because this is, I was doing this while just having breakfast. So this looks like ln of a minus ln of b is equal to y. So we quickly reminded, isn't it? Ln a minus ln b equals to y. That becomes ln of a over b equals to y. Now remember, I told you, you can't just drop the ln. How do we get rid of ln? We exponentiate, learn the word. So it's e to the ln of a over b. What you do on one side must be done on the other side. And what happens when e meets ln? Loosely speaking, if I met you out there somewhere, I don't know, shopping, and I asked you, what would happen if e meets ln? Well, they will dissolve, you would say. Very bad mathematical talk there. So a over b is equal to y. And that's exactly what's going to happen there. When e meets ln, boom, puff, gone. And so you'll have root of 1 minus x over root of 1 plus x equals to e to the y. Remember, we're solving for x, we're not solving for y. Here. And so we move that. And if I remember, we had e to the ln of root of 1 minus x all over the root of 1 plus x. Could be the other way around, it doesn't really matter, is equal to e to the y. Now you can't go drop the bases. It doesn't make sense. But we know that e meets ln, that goes away, so a root of 1 minus x all over the root of 1 plus x is equal to e to the y. How do we solve for x? Well, we got these square roots there. I don't like them, so square both sides. But you could also do the following, isn't it? Students don't like this. Ain't that cute? Yeah. And now we square both sides, and what do we end up with? We end up with 1 minus x over 1 plus x equals to e to the y. 2y, because we're squaring both sides. Cross multiply, because this is over 1. 1 plus x into e to the 2y is equal to 1 minus x. And you're going to get e to the 2y plus x e to the 2y. Plus x minus 1 equals to 0. Common factor is x, and you can see where this is going. X into e to the 2y plus 1 must equal to, take that on the other side, 1 minus e to the minus 2y, divide, and we solve for x. That's straightforward. And nothing difficult over there. All right, cool. What is happening over here? Okay. This is the neatest I've written, by the way. This is my handwriting, yeah? Okay, yes. So e to the ln of sine. Now we're familiar with this, right? Because it's a plus, so we know it's a product. But when e meets ln, gone, and the sine x drops, so we get e. Now remember, e to the power 4, it's a number raised 2.78 raised to the power 4. That's just a constant multiplied by sine x. This one very similar as well. The product, you can break it up, but we don't like the 3 there because we want e to meet ln directly. So the 3 pops up in front, that becomes x cubed. So e to the ln of x cubed becomes x cubed, and e to the minus sine x will stay there. But I don't like the minus sign. Very positive person. We don't like negativity. So we write that as x cubed over e to the sine x, and we're home. Right. Pause the video, slow it down. You don't need to rush. This is not a race. Take it easy, but make sure you understand what I'm doing. Do the problems by yourselves. Alrighty, good. What is this? Log. Now, please. There are students will cancel the log. You can't do that. You cannot. So how do we simplify this? We can't let k equal to 2x minus 1. There's no repetition here. But what we can do, now pay careful attention here. I don't like the 2 there. So the 2 would pop up in front there, right? So that becomes log of 2x minus 1 squared minus log of x plus 2 equals to log of 3x minus 4. But I'm going to write that as a 2 there because it's log of a plus log of b, then it's the product. This one is the difference. So I can write this as, write neatly as well. This is terrible writing. But I'm doing that deliberately. All into 3x minus 4. So now we're not dividing by log, but we can drop the logs here. and then we can solve for x by cross multiplying. Please try that. I think if I look at that, that's 2x minus 1 all squared over x plus 2 into 2 into 3x minus 4 cross multiply. That's going to be quadratic in x. Please, you can see there's only one solution here, which means one of the solutions doesn't work. So you've got to test your answer, because remember, log of the argument, that argument has to be a positive number. Like, for example, 2x minus 1 must be greater than 0. Otherwise, you'd run into problems. Think of the log graph. Okay, nice question. What's happening over here? Oh, right. So solve for x. Now look where the x is. This almost looks like a little problem from astrophysics. Just a tiny little branch there when you're modeling up a little star and you're looking at, say, the temperature profile of the star. As you go from the center, we know it's the hottest, and then as you get to the surface layers are much cooler, like the sun, for example. You got, what, 10 to the power 6, 10 to the power 9 close to the center, and then you got about 6,000 Kelvin at the surface. Huge drop. So, but then beta would have to be negative if you think about it. But we're not worried about that. We're looking at x. So alpha is a constant. So the first thing I would do is I would write the mirror of it, same thing, and then divide by alpha. Alpha is a constant. So you get 10 to the power beta times x is theta over alpha. The fact that's in the power, we've got to bring in the logs. We've got base 10 here, so let's bring in log rather than ln. And so we got log. What we do on one side, we must do on the other. And we know that the rule says, power rule, the beta times x will drop to the front. And log of 10 we know is 1. So this thing is 1. So you got beta x equal to log of theta over alpha. Divide both sides by beta. And they told you that mathematics was difficult. And there you have it. All right, so that's pretty cool. That's a nice question. Okay. Oh, yes. Now, these guys you have to be very careful of. And these you would have seen in school as well, right? 6x minus 5x power half equals to 6. And there's a rule, I think, it's a very silly rule. It's not really a rule, but if you have a look at the leading term here, the power is 1. And the middle term there, the power there, the index is a half. So when the leading term is twice that, 1 is twice half, then you use the k method, the Kandasamy method. So k is equal to x to the power half, right? The lower power. So when you square that, you get x to the power 1. So this guy, it becomes a quadratic in k, 6k squared minus 5k minus 6. And hopefully this factorizes. And once you've got that, then you can solve for k quite easily. All right, so you can try that and see what comes out there. And then look at this one, very similar. You got a half, this fractional powers, but a half is twice a quarter. So what do we do? Hey, reminding me of Mr. Kandasamy, my English teacher. Let it equal to x to the power quarter, because then k squared becomes x to the power a half. And then what do we do next? That becomes k squared minus 5k minus 6 equals to 0. Okay. I don't know, I got to radian measure, but I would stop there in terms of logs. And the next section up would be radian measure. But before we get into radian measure and trig, we start to prepare for our minor test 1, which is on the 7th of March. And if you think about it, that's next week. And we will be tested up to and including logs, natural logs, not radian measure and trig. So go back to TUT 0, TUT 1, 2. There's a lot of work to be done there. And that is basically recalling our high school work, or what we call pre-calculus. Right? It's setting us up for the calculus to come. Beautiful, I must say. But we would do everything up to and including logs, including equations, factorization, simplification, all of that. Don't forget, before that, we had a lot more work. It was the remainder factor theorem, long division. What else did we do? Absolute value, equations. I showed you how to draw the graph, inequalities, right? Changing the subject of the formula. Give me, oh, there we go. Can you do this one? So, Einstein, you've come across E is equal to mc squared, right? So the world's most famous formula. So it sort of goes like this. E is equal to mc squared. But what they didn't tell you is m is the mass. But the formula for mass is this. Right, where m naught is rest mass. So that's when you're not moving. But you'll notice there's an issue here. When v becomes c, that means when the particle is now traveling at the speed of light, or when the body is traveling at the speed of light, you're going to get 1 minus c squared over c squared, where c is the speed of light. Boom. So what does it mean for this formula that you're dividing by 0? Does your mass become infinite? What does infinite mass actually mean? So Einstein referred to this as mass as frozen energy, which is quite interesting. But for us, and the purpose of this course is, I would say from this formula, can you solve for V? It's one of those questions. In the tutorials, we gave you different formulae on fluid flow, other mechanics, forms of mechanics, electricity, where we ask you to change or the subject of the formula. So make sure you go through that as well. Okay, so there's a lot of work to be done. Be consistent, go through it. And I think the exponentials and the logs, especially the logs, which you didn't do too much of in school, needs a lot more attention. All right, so please watch this video, watch the previous video, and go through your tutorials and make sure you do your work properly. So take care, and hopefully you enjoyed this video. Bye for now.